In our last lecture module, we focused on the larger anatomical features of our typical neuron. In this module, we want to focus on its electrical properties and its membrane. So we're going to look at polarity or membrane potential, the net difference in charge between the inside of our neuron and the outside in the extracellular fluid. We want to look at the resting potential, the homeostasis potential that a neuron has. And finally, we want to look at the mechanisms in the neuronal membrane that facilitate moving it off that resting potential and moving it back onto that resting potential. So neurons have membrane potential, also called polarity, which is a net difference in charge measured from the inside going to the outside. So our membrane potential or polarity will be the net difference in our charge measured inside relative to the outside. And the average neuron is going to have a resting potential that is a homeostasis point where its potential, its net charge from the inside to the outside is at about negative 65 millivolts, though that can range from negative 40 millivolts all the way up to negative 80 millivolts. So this is the homeostasis point for the charge relative from inside to outside for our neuron. Now the resting potential is maintained or displaced by four distinct membrane structures. One membrane structure are the neurotransmitter binding sites, the receptors. And we'll look at those a little bit later. The other three mechanisms occur all over the neuron's membrane, and we'll look at those right now. In my diagram here, we have these thick gray lines that represent the membrane itself of our neuron, and then we have all the different circles there representing different ions inside and outside of the cellular membrane. Those other structures, the two on the left, are sodium and potassium channels. Now, when a sufficient depolarization, a sufficient reduction in the difference between the inside and the outside, a decrease in the negativity between the inside and the outside of our neuron occurs, it can trigger these voltage-gated channels to open up, allowing sodium ions to come in or allowing potassium ions to go out. That third structure on the far right there is a sodium-potassium pump. It's a mechanism that actively transports sodium and potassium across the membrane. The sodium-potassium pump will actively transport 3 sodium ions out and 2 potassium ions into the neuron. Now, as you're listening to this part of the lecture, 2 questions might occur to you. If sodium-potassium pumps are actively transporting potassium and sodium in and out of the neuron, then how is it that sodium and potassium actually travel through? What makes them travel through those voltage-gated channels? The second question that might occur to you is, I see that the sodium and the potassium are both positively charged ions. So how is it that shifting around a bunch of positively charged ions would change the membrane potential? And so we're going to answer those 2 questions in turn. The movement of ions occurs because of the electrochemical gradient. And what does that mean? Well, during resting potential, one finds approximately 20 times more potassium ions inside a neuron and about 9 times more sodium ions outside the neuron in the extracellular fluid. Now, these create concentration gradients so that sodium, which is concentrated outside the neuron, will move away from its concentration towards the area of lower concentration inside the neuron because of this concentration gradient. And likewise, potassium, which has a higher concentration inside, will move towards the area outside of the neuron that has a much lower concentration. Now, these forces, called diffusion, are relatively weak and slow. The real driver of this is the electrical part of the electrochemical gradient. Because the inside of our neuron is negatively charged, when the sodium gate opens up, the positively charged sodium ions immediately get attracted to it in the same way that the positive and negative sides of a magnet are attracted positive to negative. So that draws the sodium in. That's how we get sodium transport in at a relatively quick pace. We also have that active transport of sodium in and potassium out. And as we'll see when we turn our attention to action potentials, at a certain point, a similar electrochemical gradient will draw potassium out of our neuron with potassium efflux. And this gives us some insight into how it is that the exchange of positive ions can affect membrane potential, that difference in charge from one side of the neuron membrane to the other side. Namely, it's the amount of ions being transported, when, and how fast. And so as we go through our action potential, we'll want to make sure we pay attention to those details. Now, there's just one more point I want to make before we end this lecture module and turn our attention to the next lecture module. Specifically, how is it that a particular gate can be selective for a particular kind of ion? And what do these gates really look like? Do they look like those schematic drawings that you are putting up? And the answer to the second question is no. They are actually complex structures. They don't look anything like the stylized diagrams that I've been showing you. They look something more like this. How is it that they can select for particular ions? You know, they can select for particular ions because they have a certain dimension. And as we saw in the last lecture slide, the particular ions have a size, and so only ions that will fit through a particular sized gate will be allowed through that gate, and so it serves to filter out the other ions on the basis of selecting for size. In our next lecture module, we'll turn our attention specifically to action potentials and talk about how a neuron initiates an action potential from the very beginning of it to the very end of it.